All right, this is the second 2007 question, Form B. And so let's look at it. They have a fuel cell, and they tell you the fuel cell operates at a certain pressure and temperature, and for a certain number of minutes, which might kind of hint that we might do a deposition question later on. And they tell you this is how many moles of oxygen are actually used in the reaction. They want to calculate the volume of hydrogen consumed during the same period. So I don't think most of this is going to matter. We know how many moles got consumed, so we should be able to figure out exactly how much hydrogen was consumed just using stoichiometry. So in the reaction, there are 2 moles of hydrogen for every 1 mole of oxygen. And so what that means, therefore, if we are using 0.0746 moles of oxygen, then we got to have twice that many moles of hydrogen. Alright, and so according to the balanced equation, we said this was the ratio, and therefore this is how many moles of hydrogen are needed to consume that much oxygen. Now that we know our moles of hydrogen, it's simply a matter of doing PV equals nRT to get the liters, and so we're solving for volume. Volume equals nRT over P, and then I'm going to plug in our values. And so here it's all plugged in, and I get 3.65 liters for the answer to part A. And I think it should have 3 sig figs because the 78 does, the oxygen does, this does when you add 273 to it, and the atmospheres does as well. Alright, in part B, they want to know, since this is the reaction, write the 2 half reactions that occur as the cell operates. And so it seems pretty simple, like you might just go hydrogen goes to water, or you might be tempted to do H+, and for the second one you might say oxygen goes to water as well. But remember that that whenever we're doing either electrolysis of water, which is the reaction that's reverse of this, or going the way that we're going here, it's a good idea to balance these out. And you notice that we could balance them right here as they are, or since the people who took this year had a reduction potential table, it's simply a matter of just looking up what the reaction is on the reduction potential table. So on the reduction potential table, it said that there were 2 waters, 2 electrons, the hydrogen, and there were 2 OHs here. Although it's done in acidic medium, so we might need to fix the OHs in just a minute. Let's see, the other thing is the oxygen half reaction according to the reduction potential table has oxygen plus 4 H pluses plus 4 electrons, and it goes to 2 waters. So we've got these written down as they'd appear on the reduction potential table. I forgot to mention that while this bottom one is complete, and when I looked it up in the table I didn't have to flip it, the top one here was written in the reverse form, but you remember that we got to draw the reaction as it's indicated up here, and up here the hydrogen is becoming water. So this one I did end up flipping. The other thing is, since it's done in acid, I doubt they're going to let us keep this OH. So you remember we're going to get rid of that, and we're probably going to have to rewrite it down by adding 2 H pluses here, sort of the reverse of what we might do if we were doing this in base. And then of course these are going to come together to make 2 waters. And so we're going to get 2 waters plus H2 goes to 2 waters plus 2 electrons plus 2 H plus. And then we can get rid of our waters, and we just end up with H2 goes to 2 electrons plus 2 H plus. So that's probably the half reaction written in its acidic form because it was in an acidic medium. Now in B part 2 they say identify the half reaction that takes place at the cathode, and You know, I should stop here and mention, by the way, you see how messy this is? It's because I have limited room. You definitely would want to rewrite it and then box your final answers in kind of the way I did there and there. So let's look at 2. Identify the half reaction that takes place at the cathode. Well, we know that the cathode is where where reduction occurs because of red cat. And so we just got to identify which one's reduction. I don't think it's the hydrogen one because it's going from 0 to +1. That seems to be losing electrons. That's oxidation. So I think this reaction is going to be the one we're going to identify as the one occurring at the cathode. You notice they don't say to explain it, so I think that that would be good enough to point it out and maybe redraw it down. Then in part 3, it wants us to determine the value of the cell potential. And so we already looked up these 2 reactions, and you remember that this second one, well, let me remember this, number 1 and number 2. So reaction number 1 was written exactly as it was in the table. So if I were calculating the cell potential, remember that I need to add together reactions number 1 and number 2. And number 1 was 1.23 volts. And number 2 was written exactly backwards. They have negative 0.83, so I'm going to do positive 0.83. 0.83, there's not a lot of room here. And then I just have to add those 2. So I get 2.06 volts. And checking sig figs, we got these from the table. They both go to the hundredths place since we're adding. And so we're going to keep it at 2.06 volts. And then lastly, part C, calculate the charge in coulombs, which is pretty much amps, but we'll see how that goes through. It's definitely a deposition question because they give us time. You notice they don't give us amps, so I think that that's what we're going to be doing. So remember that we always start with time in the beginning, so, and we're doing C, 78.0 minutes. We convert minutes to seconds. And then normally we'd have amps, and we'd have the number of coulombs per second. And I think that's what we're going to be solving for. And then we know there's 96,485 coulombs per mole of electrons. That's Faraday's constant. And then we get to the point where we got to convert moles of electrons to something. And you notice they're not specifying what it is that we're moving it towards. But you notice that we knew some things up here. We knew how many moles of oxygen got produced. And so if we went to moles of oxygen, then we could say that it produced 0.0746 moles of oxygen. You notice normally we go to grams, but here we don't really have to. So I wrote the reaction back down because we need to know how many electrons each oxygen needs. And so you notice that our one oxygen in that balanced half reaction accepted 4 electrons. And so that should be the answer there. Incidentally, the year they did this on the key, they accepted 2 here, and I'm not sure exactly why, because you can clearly see from the balanced equation it should be 4. But for some reason they accepted both answers. So now I'm going to solve for x. So I multiplied all the numbers, and that's what it came out to be. It's still times x equals our 0.0746. And when I solve for x by dividing by 0.01213, I get 6.15 coulombs. And let me look at sig figs here. That certainly at 78 minutes had 3 sig figs in it. What else did we need in here? Time's a pretty exact number, so we don't need to worry about that. This has more sig figs, and the 4 is an exact number. So I would say 3 is an appropriate number of sig figs.